So to continue with the saponification reaction, if you do the same reaction with fat or oil, doing the basic hydrolysis, what you get out is 3 fatty acid salt and glycerol. And the reason why you get an acid salt rather than a carboxylic acid is you know that these 3 fatty acids, the carboxylic acid functional group, these protons are acidic. So what's going to happen under basic condition, okay, remember there are a lot of base around, the acidic proton is not going to stay around, but it's going to be deprotonated doing an acid-base reaction, and that's why you would get an acid salt. So it would have RC-O minus with some kind of metal, like sodium or potassium, whatever base that you use. If you use sodium hydroxide, you would get a sodium salt. So that would be the product, and this is basically the basis, and I'm sure you remember this when we went over the saponification reaction with esters, that this is the basis of how soap and detergents are made. All right, so you take animal fat or oil, vegetable oil, doesn't matter. You take some kind of triglyceride and you react with a base, and what you get is acid salt. And the way soap works the way it does is because it has dual properties. So if you look at the acid salt carefully, notice that the R portion is very long in this, so that is going to be non-polar. And then you have at the end carboxylic acid salt, because of the charge, the ionic part causes this little portion to be polar. So what happens when you have a grease in your hand and you want to wash it away, if you just take your greasy hand and put it under water, you know that the grease doesn't go away because water doesn't like the grease. You have hydrophilic water with hydrophobic grease. But soap allows the grease to be washed away, and the way it does that is that if you pretend that this in the middle is the grease on your hand, when you put soap on your hand, then all these molecules, soap molecules, will form a micelle, okay, in which the grease is in the middle. So think of this as a cross section. So you're looking at a 3D, like a ball, like when you think about it. So inside that ball is a grease in which the soap molecules have surrounded all around, and because grease is going to be hydrophobic, the tail is going to point in, so surrounding the grease with all the tails of soap molecules, and what's being faced out is the polar portion, the hydrophilic portion. So then the water only sees now the hydrophilic portion of the soap molecules, which then is easily removed when you wash with water. And that's how it works. And the dual properties is very important to remember when we go later on talk about the lipid bilayer, phospholipids, etc. Okay? And the third reaction that we're going to look at is a hydrogenation reaction. And you know from Chem 114 that double bond or alkene and alkyne, you could hydrogenate with some kind of catalyst, and you are adding 2 hydrogen atoms, a mole of hydrogen across the double bond, and so you're going from alkene to alkane. All right, and this is the process that is used in the industry, and that's called hardening process, in which when we take vegetable oil that has double bonds in them, right, and you do hydrogenation, then you are making sort of slightly solidy compound. We call that margarine, and we substitute that a lot of times instead of butter, so that we have less cholesterol. But so the reaction that you're looking at is, let's say this is a molecule of oil, as you see the cis double bonds, and after the hardening process or the hydrogenation process, all the double bonds are gone, and you have the saturated. All right. So the hardening process, they monitor it so that it doesn't. They don't all become saturated. Otherwise, it would be really, really hard. So they partially hydrogenate to the right consistency that you want. Okay. Probably the biggest controversy about these margarine is the fact that there's trans fatty acids present. So it turns out when you do the hydrogenation, some of the byproducts of the hydrogenation is that instead of having cis double bond, you have trans double bond. Okay, and the reason why I have this picture is this is the normal fatty acid with the cis double bond, and look at the shape because of the double bonds being cis, that's naturally occurring. Okay, so if these double bonds isomerize to trans double bonds, then this is what it will look like. And notice how similar it looks structurally to the saturated fatty acid, right? But so it's shaped like a saturated fatty acid, but the problem is it's got a double bond in it, so its reactivity is going to be similar to the double bonds, not to the saturated. So a lot of scientists think that the trans type of fatty acids, they raise the bad, the LDL level, and there's a lot of controversy about whether or not this is okay or not in your body. All right, but this is basically a man-made, if you will, fatty acid. And speaking of man-made fatty acid, another one is cholesterol. And as we looked at briefly before, instead of glycerol being the alcohol backbone, in cholesterol you have sucrose as the alcohol backbone, and you have anywhere from like 6 to 8 fatty acids on this sucrose. And there was an interesting article in Time magazine a couple years back about, are we ready for fat-free fat? And this is part of the problem with, this is the article, part of the problem with the fat-free fat, cholesterol, is that look at the size difference of a normal fat with a triglyceride, and our enzyme is able to go in and metabolize it, but this is the size of cholesterol with the sucrose as the backbone, and because it's got so many fatty acids attached to it, the enzyme can't get in. There's no room to be able to cleave it. So that's why it doesn't give you the calories, and that's why it's fat-free fat, and it tastes good. But the problem is this doesn't get metabolized, and it goes right through your system. And because it's hydrophobic, it acts like a solvent, if you will, hydrophobic solvent, and it depletes your body of vitamins and things that are hydrophobic. So that's one of the big problems with using fat-free fat, and many of the people have problems because of that. And I don't think this is healthy way to diet. All right. So at this point, you should be able to give me products of this. Your book doesn't do the reduction, although you should be able to do the reduction, but you don't have to do that problem D. But it would be a good practice for you to do that problem. But if you don't want to, then you could skip that. But you should definitely be able to do 26.4, 26.7, and 26.9. I'm going to end the lecture here because next lecture I'm going to look at other type of lipids. So we'll stop this lecture here.